to hear about all this very cool science. I debated about what to talk about, but I decided to talk about mantis shrimp. It is one of the things I talk about a lot, but I'm gonna tell you a lot about tonight are things that I don't normally get to talk about. And maybe you may be familiar with mantis shrimp and some of their really cool, weird biology, but I'm hopefully gonna tell you some things that maybe you didn't know about them that make them even cooler. So just, again, my name is Megan Porter. I'm faculty at the School of Life Sciences at UH, and I study the evolution of animal vision, but really my heart lies with stomatopods. They're where I sort of got started in vision, and they're really cool animals, which I'm gonna tell you about here, maybe. There we go. So just if you aren't familiar with them, they are an order of marine crustaceans, most commonly associated with coral reefs, most of the diversity, and they have some really unusual biology. You can see from this pair of Odontodactylus stylaris that they could be very, very colorful. There are over 500 species described, and just for some local context, there are over 20 species known here just from Hawaii, with a couple of species we think are new that we're working on trying to describe and name. You're only likely, they can be very cryptic though, so you're only likely to see, if you're out there, maybe 1 or 2 species, most commonly. But as we get started, I have the understanding that some people might like to drink when giving these talks. So I am providing you a drinking game, should you like to follow along during the talk. And so what I'm gonna do is I'm gonna go through sort of 5 topics and tell you a little bit about stomatopods, their biology, why they're cool. And then with each one of those, I'm gonna give you some fun facts that maybe you didn't know either about their biology or about some of the bio-inspired technology based on their weird biology. So every time I give you a fun fact, feel free to take a drink of your favorite beverage, all right? And maybe at the end, you'll decide that mantis shrimp are your new favorite animal. If not, you need more convincing, you can go and check out a cartoon drawn by the Oatmeal a number of years ago now, but still very relevant and worth taking a look at. So first, we're gonna start off relatively easy to give everyone some practice with this drinking game thing. So the first thing area I'm gonna tell you about mantis shrimp are that I've already told you they're coral reef shrimp. I'm gonna talk a little bit about their sort of vicious nature in a little bit. This gives you a preview of that, this image. They are known for being predators, which is unusual for a crustacean, and being very good and sort of lethal predators. But they're also culturally important around the world, which many people don't realize because they aren't really in the US. And you can see that in a number of different ways. So there are a number of countries that have featured them on stamps, which I think is, that means that they're recognized, right, by local populations. You'll see parts of their appendage that they use to capture prey with in jewelry. So here's just a pair of earrings, although be careful, they are still very sharp and will hurt you. So if you get a pair of mantis shrimp jewelry, just make sure you wear it cautiously. You see it involved in some weaponry. So here's a piece that has all of these sort of spiny things along the edge of this weapon are mantis shrimp dactyls. So the part that they catch fish with. These spikes along with some shark's teeth in the middle there. And then there are certain parts of the world where you will see mantis shrimp on the menu commonly. So you can find it as sushi in Japan. There are parts of the Mediterranean where you can find them in the fish market. And your first fun fact for the evening is that I have been told by a very reliable colleague who knows many, many things about mantis shrimp that the original shrimp scampi in Italy was based on mantis shrimp. So next time you go to Italy, maybe stop by Venice. If you're there in the right season, you might get a mantis shrimp scampi. If you do, take a picture and send it to me because I would very much like to see documentation of this for myself. But so that's your first fun fact. Next time you have shrimp scampi, imagine it full of mantis shrimp. All right. The second area I want to talk to relative to mantis shrimp. There are two things mantis shrimp are really known for. The first one, and that's what I'm telling you about now, is their crazy vision. So they have these beautiful eyes here. And this is what I study, so I could talk about this for hours and hours, but I'm not going to do that. I want to tell you a few important pieces of information so that I can tell you some things you might not know about their visual systems. So why do we say they have crazy vision? They have crazy vision because they can detect at least 5 times more colors than any other animal that we know of. So for comparison, on the top there is the human visual color vision system. So each of those curves represents the sensitivity of one of our types of color photoreceptors. So we can detect 3 colors, blue, green, and red. And from comparisons of the input to those photoreceptors, we can see this broad array of colors. Mantis shrimp, we know they can detect 16 different colors across the visible spectrum. So each one of those curves on the bottom is a sensitivity measured from a photoreceptor and stomatopod eye. So you can see they have many more types of photoreceptors that are spread out across the visible spectrum, including at least 6 down in the UV part of the spectrum. So down in the 300 part of the visible spectrum where you've got those gray curves, those are UV. So they can detect UV of different types. So for many, many years, including when I started working on stomatopods, many of us who work on them were like, what in the world do they see? They must see so many colors that we can't even imagine. It's got to blow the mind. So your next fun fact is actually a disappointing one, not to burst the bubble of the amazing stomatopod vision, but they actually see fewer colors than humans. They are worse at discriminating colors than we are. It's very sad, I know, but it does seem to be the case based on behavioral work done by Hannah Thoen, who did some very detailed color discrimination tests. But the really cool thing about that is what it means is that they have very different ways that they process visual information. So we see colors because we have big brains and we can compare the input to different photoreceptors. So we don't have a yellow receptor, but we can see yellow because we compare the inputs to red and green, which are different if we were looking at something that is yellow, right? What stomatopods do is they just send each one of those individual pieces of color information straight back to the brain. There's no comparison. So it's a very fast system, but it means that they can't see the in-between colors. At least that's how we think it works. So that was really surprising after many, many years of trying to imagine what stomatopods could see. Something else you may or may not be familiar about with mantis shrimp vision is that they're really good at detecting polarized light. So this is light that sort of vibrates all in the same plane. And in this image, there are people who study stomatopods who have tried to develop cameras based on the way that stomatopods detect polarized light. And so using those cameras, the image on the left is a beautiful little haptosquilla hanging out in its burrow. The one on the right is taken with one of these polarization cameras that shows you the degree of polarization. So how polarized is the light coming off of a surface. And the orange arrow shows to those, like on the right there, there's really bright sort of red bean-shaped things. So those are structures on the stomatopod that are reflecting highly polarized light. So they have this sort of secret communication channel that they can use underwater. And so, there are a number of species who use polarized parts of their bodies to communicate, often in the context of mating. Again, secret signaling, but in sort of close communication. Fun fact number 3, this is another sort of bio-inspiration from the weird stomatopod biology, because they're so good at polarization specialists. There are bioengineers who are working on designing a camera based on the way that stomatopods see polarized light and using that to detect cancerous, sort of precancerous cells. So apparently cancerous cells give off a polarization signal. It's still in development, but it's a really interesting idea and something that has come from the way that stomatopods the way their eyes are set up to detect polarized light. All right, number 3. This is probably what stomatopods are most well known for. They are lethal predators. That sort of mode of predation comes in 2 forms. They can either, there are a number of species that spear soft-bodied things, or a number of species that hit really hard. And they've been doing this for a really long time. So you can find up in the right there is a fossil stomatopod. So hundreds of millions of years, they have had this sort of predation mode. And they are one of the fastest and hardest strikes in the animal kingdom. The smashers in particular can hit with the force of a .22 caliber bullet. If you want some of the stats recorded by Sheila Patek's lab and many of her studies for exactly what that means in terms of this, how fast it's moving. They also are moving so fast that they produce cavitation. So this is where they basically vaporize the water. They're moving so fast through the water, they vaporize it, leaving a void that then collapses on itself and creates a shock wave. So they have the initial force of their hit as well as the shock wave of the cavitation behind their force. So they really are good at destroying things. Fun fact number 4 is that even the baby stomatopods are lethal. So this is work that is actually in review now with Sheila Patek's lab. And I'm going to show you a little animation of this cute little stomatopod. We found out originally Eve Robinson did this work. Oopsie. And I have a little, I can make my stomatopod dance. But to show you that strike, because I don't have a video of it set up, if anyone needs a dancing larval stomatopod, I got you covered. But so they are lethal perhaps to tiny planktonic things. We haven't actually observed them catching anything. We assume they are using it to catch prey. But even the tiny ones have this really fast strike. And that's something we're still trying to figure out. Interesting stomatopod biology, point number 4. And so maybe this is logical given that they have really, they're really good predators that can hit really hard, that they have a really strong exoskeleton, right? So they not only hit their prey, they also have interactions where they fight over burrows. So they fight with each other for space. And so they are not, sometimes they are directing these really deadly blows towards each other. So that means, one, they have to be able to withstand that, but there are some interesting questions, biological questions, about how something that hits so hard and fast that it produces cavitation, how do they keep from, one, killing each other every time they fight, but also destroying their own appendages when they strike? And so there's been some work done on that. And I should say, in these contests, there's been some behavioral work, some really great behavioral work by Patrick Green. You should go look at his work, that show that in these sorts of contests, it's not the shrimp who hits the hardest that wins, it's the one who hits the most. So if you can just keep going, kind of like a boxing match, it's more likely that you're going to be the winner. But so there are a number of sort of biomaterials, bioengineers that are interested in this exact question of how do stomatopods hit so hard and they don't destroy their own appendage. And it turns out that particularly that dactyl part, so that white arrow points to the part of the stomatopod raptorial appendage that is hitting things, that pink bulb on the end there. And if you look at the material in that carapace there, in that exoskeleton, that part of shell, it has a really interesting sort of twisted a series of twisted cracks that give it that make it lightweight, but also give it the strength to hit really hard without cracking itself. It can absorb that shock. And so this is a really interesting structure people are interested in. For fun fact number 5, which is that this sort of unusual material property that comes out of this sort of series of twisted structures is incredibly lightweight and incredibly strong. So there are people that are studying it and trying to develop, take what they've learned from the stomatopod structure and develop into things like lightweight airplanes that are resistant to bird strikes, and body armor for combat troops and things like that. So yeah, there's a lot going on in the mantis shrimp. All right. And then the final area of mantis shrimp biology that I wanted to end on is just, so we've talked a little bit about their complex vision, a little bit about their strikes and their sort of unusual properties of the striking appendages. I wanted to sort of end up biologically anyway on some multimodal communication. So you've seen lots of colorful pictures about mantis shrimp. And so they are colorful. They also have some additional secret modes of communication in addition to that polarization. So in this picture, if you see those purple spots, those are on the inside of the striking appendage. And so they can flash those if they want to another stomatopod. And it turns out that those are sort of a species color code. So if you look at different species, they have a rainbow of different colored spots that are specific to that species that are found in that position on the inside of their fighting or prey catching arms. But in addition to some of these ways that they communicate with color and polarization, fun fact number 6 is they also talk to each other. So there are a handful of species that live in burrows that communicate using a low frequency rumble. I don't know if this is going to work, but can anyone hear that? No, can't hear it. I'll have to send you the link. It's really impressive. I can hear it. It's great. I'll send you the link in the chat later, but you should listen to it. So they use these low frequency rumbles, they think, particularly when males and females that live together, the males hunt. If they get picked off or die, the female can then advertise without leaving the burrow, the safety of the burrow, that she's looking for a new mate to come and hang out with her. All right, and the final fun fact, I know you're not gonna be able to hear the sound on this, but, and I know videos don't play well, but hopefully you'll be able to get a sense of stomatopods and whether or not they're good at puzzles. This comes from a documentary, David Attenborough narrating, which is always a good sign, called The Fastest Claw in the West. So if you ever wondered whether or not stomatopods are good at puzzles, there's your answer. And that's all I got. So I'm happy to answer questions. Hopefully you learned a little bit of something about mantis shrimp that you were unaware of before. Thanks for listening.
Woo! Woo! For having me, Marissa, and hello, Nerd Nite. It's my first one. I'm actually working in the marine biology graduate program focused on sharks. But that's kind of how I came about this topic. And don't worry, there'll be some sharky stuff in there for you. If anyone wants a drinking game, go ahead and have a sip, whatever you like, every time I say the word Eddie. So a couple of the cool things that ocean eddies are responsible for. We're going to make 3 big connections and look at some future projections. But they're responsible for texturing the sea surface. So this is looking at a distribution of anomalous texture to the sea surface. And one of the most important currents, which we'll find out later why that's so, is the circumpolar current. So down there around Antarctica. It's important to remember that the Arctic is ice and the Antarctic has some land mass below it. But we'll get into some more fun stuff. We'll see if this video works, and if not, that's all right. But if you guys are seeing it, we have some credits due, and we're gonna see some sea surface temperature change around one section of the Antarctic eddy field. This shows in Celsius, so I did some conversions. Fahrenheit, Up at the top where it's kind of red, you're looking at 64.4 degrees Fahrenheit, and this big temperature gradient or Antarctic margin where we're seeing this transfer down to -2 degrees Celsius or 28.4 degrees Fahrenheit, but also just some visualization for current speed and then velocity, just so you guys are seeing a visual of what an eddy is. It's really hard when you look at pictures on charts and papers and things, they're not very dynamic. So they're basically spin-offs of these large currents, or they can be wind driven, and they can kind of spiral out and then remerge and redistribute things like nutrients, heat, chemicals, even larvae, stuff like that. And they can actually go quite deep. So transferring even energy down sometimes to the seafloor. Okay. So first we have a look at the eddies can spin in 2 different directions, and then they're mirrored from the northern hemisphere to the southern hemisphere. So just below the equator on the top picture, and then above the equator on the below picture, these are both anticyclonic eddies. What you typically see is the cyclonic eddy moving counterclockwise, just like the rotation of the Earth or the atmospheric cyclones. The reason the top picture is moving counterclockwise and it's anticyclonic is below the equator. And between the size of the arrows and the direction of the arrows, you can see that movement westward, and down below the eastward movement of the anticyclone above the equator. Sharks, I can't stay away from them. They're the focus of all my master's studies. And so first we have 2 cases looking at first blue sharks and the way that they actually are using the heated core of an anticyclonic eddy to access a magnitude higher scale of prey. So this might be confusing to look at altogether, but the reds in all of these figures are the anticyclone eddies, so spinning clockwise above the equator. And they have kind of this ability, we'll see in the next figure, to pull heat down and to bring things from the surface lower, whereas the counterclockwise of the cyclone, it kind of pulls heat and maybe upwelling things from deeper up higher. So these blue sharks in particular are encountering both cyclonic and anticyclonic eddies, but they're actually foraging. So on C and E, we're looking at random walk simulations, and D and F are the shark movements themselves. So their focus there, from the x-axis, the distance from the eddy center, they're focusing on their foraging zones into the core, the heat zone of the eddy, because that's where their thermal constraints are. So A and B, you can get a visual of that kind of ability for just in even a couple degrees to be brought up in a cyclonic eddy or brought down in an anticyclonic eddy. And then in C and D, it's important to note that the number of dives that we're looking at for these 2 profiles are 7,271 dives into anticyclonic eddies, and then 2,521 dives into cyclonic eddies. So an overwhelming number into the anticyclone eddies. And to further clarify, there's some little black boxes that are in the cyclonic category, and those are actually Sargasso Sea. They're eddies that began in the Sargasso Sea, so they're actually more resembling the anticyclonic makeup, and they have a warm core and not a cold core. And then in E and F, we see the blue sharks are predominantly diving down deeper. So this is like about 600 meters at the very deepest in the daytime. So you have a little bit more access. And for comparison, this was only 2 mature female white sharks. The previous case study was 15 blue sharks over a much longer time series and dive profile. But we're still seeing this is kind of a precursor into the work just specific to sharks, that they have these thermal constraints in there, and so that's what's enabling them to go deeper, is the heat in the anticyclone. However, something to point out is in the open ocean eddies, these white sharks were diving predominantly at sunrise and sunset, and they're able to go day and night. You can see in the bottom right corner, because actually the white sharks have the rete mirabile, so they can kind of keep their core temperature a little bit higher than other sharks can with that series of blood vessels. Okay, so deep sea. This is actually the course where I started this topic of eddies. I caught on to it from sharks, and then my first presentation was nowhere near as good as this one. But it was focused on the deep sea. So we're looking at first this ability, well, it's not an ability, but it's this concentration of movement that forces this kind of downward velocity within an anticyclone eddy. And so we have two different currents. We're looking at a current off the Western Australian coast and also in the Mediterranean Sea. And in the C and D subsets for figure 1 and 2, we're looking at a difference in particle size. So there's also this difference in concentration of things from 0.06 to 0.53 millimeters in the small particle category, and 0.53 to 1.06 millimeters in the large particle category. So small particles in C, large particles in D. And the biggest distinction is, first of all, the orientation of the smaller particles closer to the surface. So in the heat map, part of that wine glass theory is the shape of the concentration of these particles that's created within the eddy. And then what you can see in the D categories is there's a gradient of these particles deeper. And another way I like to compare these two, C, they look like a wine glass, and D, they're a little bit steeper, more like a margarita. So anyways, then further down on the bottom, you can see more of that velocity simulated model of this kind of pull down. Again, this is the anticyclone, so the heat coming down, supposed to be cyclonic eddy pulling up, which we can see in a movement of deep water sediment. So this is a couple, 2,100 meters anchored at the bottom of the South China Sea. We're seeing this pull upward, not only of deep water nutrients when you think of upwelling, but sediment that's being redistributed. And so that's a little bit of a stretch, but it could be tied to some case studies involving distribution and biodiversity of nematodes and isopods. Is that my other note? Anyways, down on the benthic floor community. But also, this was my favorite one probably, is a look at hydrothermal vents. So this is a case study done in a mid-ocean rift, and she was looking at larval distribution. Basically, how are these larvae making it to these volatile hydrothermal environments? And if you look in the charts above, at March, you see this distinct shift from gray bars to white bars, and it's really shown in letter C, the observed velocity, where you can actually see that eddy take over, and these really high currents, there's a lot less larvae coming down into these POC flux, the traps that they're using to measure. And so the point is, you're seeing these deep water roots and these deep water eddies now in a couple cases around the world that can go literally from the surface and have their effects felt all the way to the sea floor. And just for a quick follow on, this is kind of a look at upwelling in the higher latitudes, the northern latitudes, and kind of the pink. And the depression looking towards the blue is actually looking more at downwelling to kind of understand this depression and the carbon cycle. And I'll continue on into the Hawaiian archipelago, because Hawaii has a rich history with eddies. We have this really cool system in the lee of the islands, especially right now behind Haleakala, or around Haleakala and Mauna Kea. And so it creates this really strong funneling of wind when you're looking at how high these volcanic forms go, but also kind of deep water when you're looking into current movements as well. And it creates these asymmetric patterns of cyclonic and anticyclonic eddies that have been shown to concentrate things like micronectrons, and potentially have effects on larger pelagic fishes. So that's kind of a gap, which was touched on with the sharks, but there's not a lot of concrete connection between the use of the pelagic fishes and the use of these eddies. It's still kind of a debated topic, in fact, whether they're using it as migration cues or they are, specifically finding these or seeking these anticyclonic eddies and diving on them. But in a 1995 billfish tournament, it was a really interesting scenario where there were these patterns of eddy formation, and these huge marlins being caught. That was really unique. Again, they're not full connections, but they're things that we're considering as people further study eddies. And another one that I wanted to touch on, another gap in the field, is this kind of acknowledgement of indigenous knowledge, because from my previous experience, I'd heard of these things called floating islands, and the metaphor in Mo'olelo as being maybe tied to this reflection of a cloud over an atoll. So in this picture, that green in the middle is kind of breaking up the cloud, and you can see the green reflected on the cloud and then back down in the water. And so for a wayfarer, that could be a farther navigational aid into, okay, there's an atoll there, there's land there, there's something going on. But what's been more recently introduced to me was this concept of, eddies are fairly regular, although they're anomalous. They have these regular fields that they're common in, and they're congregating things up the food chain, so planktons, potentially interactions with larger pelagic fishes. And so maybe the eddy itself could be this conceptualization of the floating island, which is a global legend, actually, not just unique to Hawaii. Now, something important to note in Antarctica itself is that circumpolar current, which in the last decade or so has been decreasing. And also alongside the decrease in the flow of the circumpolar current, we're seeing this rise in the eddy field, and also this rise in the wind. And we could be looking at, the ability for these eddies and this heat transfer to be having this interaction from the slope to the shelf and actually moving heat up and underneath of the ice from where it meets the land. So that's kind of could be, I guess I should stick to the facts. It has implications for circulation, carbon cycling, and climate. I don't want to draw too many conclusions without adequate support. And then one more gap in the field, which came up from my previous kind of go at this presentation. These eddies, here's some of the case studies that I highlighted in this talk, or ones that I was researching in the field in the topic. And so they're global, and we know that eddies are global, but these are also, the arrows are indicating these deep reaching eddies. And so just remembering in this conceptualization of, like, when you look at a map or a chart and there's this whole just, looks like a big lake called the ocean, there's so much going on and there's so much dynamic transport. And so are there connections between these eddies and these fields, and are they perhaps a conduit for things like microfibers? So in the now, we are dealing with climate change, we're dealing with plastic distribution, and you don't have to read any of that stuff. It's just in case you guys are unfamiliar with plastic and breaking down microplastics, nanoplastics, a degraded pair of jeans down below. But we're faced with these high concentrations of plastic on the surface all around the world, and we're seeing things like microfibers turn up way down deep as well. So perhaps the eddy could be a conduit. Since we can measure particle transport, we can measure the transfer of energy. So really, that's all I have to share with you guys. Hopefully you learned a lot, learned a little, and are that much more keen to pay attention, or I don't know, just keep eddies in your mind.
Woo! Can everybody see that? Okay.
Yes, looks great.
Okay. Thanks, Nerd Nite crew, for inviting me to give a talk. I'm Jaynee Kim, and I'm one of the collection managers at the Bishop Museum Malacology Department. Today I'll be talking about 2 snails that we actually got to describe and name this year. Oh, I think I'm having some difficulties. Hold on. There we go. Okay, so naming the new species, it's a fundamental step when describing biodiversity. And it's the only way to ensure that everyone, whether scientists or the public, is talking about and comparing data of the same taxa or group. And without a name, you also can't put them on any conservation list, and therefore will not have any management plans developed to ensure its survival. So I have a small quiz for you, fun quiz. If you get the answer right, you can take a drink. If not, take a drink anyways. So can you guys tell me how many new species are described daily? And I guess shout it out or put it in the chat.
15.
6.
Close. Okay. Good guesses. Oh. 2? 2? So it's actually about 50. And over the last decade, there were about 10,000 to 18,000 new species described each year. Okay, and can you tell me how many species extinctions occur daily?
200.
2. Any other guesses?
100.
Very close, yeah. So there are about 150 based on extinction estimates. So how long do you think it takes to describe a species from discovery to description?
5 years.
1 year.
A little longer?
2 years.
So it's actually 21 years between discovery and description. And they call it a shelf life, as these specimens are sitting on a shelf until someone gets to them. Not only do we not have enough time, we don't have enough people to be describing and naming these species. We also have a taxonomic bias regarding the groups that are studied and where they are being studied. So you can see this map here showing the number of papers from each of these areas, a number of conservation papers. And so there are a lot more coming from places like Europe, Asia, North America. And then you can also see the taxonomic bias, where invertebrates get less attention than vertebrates. So millions of specimens are housed in natural history collections, and among them are numerous species to be described. Some have been waiting for more than a century. At the Bishop Museum Malacology Collection, we have about 6 million specimens, many representing threatened or extinct Pacific Island land snail species. And some of these are undescribed. And you can see, oh, sorry. There we go. You can see a range of the land snail species and also marine snails that we have at the museum. So when Solom assessed the Hawaiian land snail fauna in 1990, he worked extensively in the Bishop Museum collection. And he estimated that there were at least 200 undescribed Hawaiian endodontids. And currently only one of the 200 undescribed species have been recorded alive over the last 4 decades. And you can see the little guy over there. So we all know that we're in a biodiversity crisis, and it's pretty bad for Pacific Island land snails. In recent decades, species are often described after their extinction when it's too late to conserve them. The last living land snail species was described in 1960 by Cookin Kondo, and this species is Philippoa singularis, and it's about the size of a grain of rice. Over the last 15 years, we've conducted over 1,000 surveys searching for the remaining Hawaiian land snails. And we've recorded about 300 species so far, and estimate that about 10% are still undescribed. So here are a number of the native Hawaiian land snails, some that are most of which are only found in Hawaii. Several of these extant undescribed species have been awaiting formal descriptions for more than 100 years. Oh, sorry. And one such species was first discovered in 1912 by researchers at the Bishop Museum and recorded alive in 2013. Using an integrative taxonomic approach assessing conchology, genetics, and reproductive anatomy, we finally described this new species. And the new species was described and compared to the type of the genus as well as other members within this genus. In honor of longtime champions of Hawaiian biodiversity, Wayne and Betsy Gagne, this species is named Auriculaella gagneorum. Wayne passed away several years ago, and Betsy passed away earlier this year. Betsy has a long history with the Bishop Museum Malacology Department, and we will miss her greatly. Here's another species that we recently described, and this snail has been without a name since being discovered in 1923. We hope you enjoy the Star Wars image that my colleague Noreen Yeung created. So this species is found on this tiny island in the northwestern Hawaiian Islands within the archipelago. And it was discovered during the Tanager expedition. And like other snails found on this island, they're hunkered down in the base of this, this native grass. Using the same integrative approach, combining morphology, genetics, and biogeography, we recently described this species. And you can see some of the cool conchological characters in this SEM image, the teeth or the lamellae in the aperture of the snail. Also the internal anatomy that we dissected out. And this is a picture of the radula of the snail. So it's the teeth of the snail that they use to eat with. So we named this species after Carl Christensen for the many years he devoted to studying highly endangered terrestrial mollusks from the Pacific Islands and especially the Hawaiian Islands. And both Carl and Betsy started off their malacology experience as high school interns at the Bishop Museum Malacology Department almost 50 years ago under Yoshio Kondo. And Carl continues to be a treasure trove of land snail knowledge, and we just really appreciate all that he shared with us. So as exciting as it is to describe new species, Unless there are conservation strategies in place to protect these species, they both face imminent extinction. And currently, there are only 3 populations left of Auriculaella ghaniorum. And you can see on this map, the gray is the historical range and the green is the current range. And you can see that the range has really shrunk. Endodonta christianseni is also the last known live endodonta species on Earth. It's found, this genus is found nowhere else, and it's only found on this species is only found on Nihoa. So a single hurricane or other calamity could wipe out these species, and this would represent the irreversible loss of an entire lineage, unique lineage, and with it millions of years of evolutionary history. But there is hope, and in naming them, we have given them the recognition needed to conserve them. So with an estimated 7 million species awaiting description and an extinction crisis on our hands, we must address the taxonomic impediments to conserve the remaining biodiversity, with one of the first steps being providing a name. And as one of the Hawaiian cultural practitioners have said, when we give it a name, we give it life, and we recognize its significance. So the next step is to educate people to care beyond the charismatic megafauna, even though, as you see, I really love them. This was a drawing made by Betsy Gagne back in 1981. And we see so many of these poster children for saving biodiversity, the whale, birds, the turtle. But to truly save it, we need to start caring about the plants and the little things that make up most of biodiversity, like the inverts. And with that, I'd just like to thank all of these people. We've built a network of national and international collaborators over the years, and we couldn't have gone far without a lot of their help. And also the various funding sources and partners. And with that, I'll take any questions and leave you with a video of a cute snail.
Woo!